I think that we can start.
Okay.
So, what? So, dzień dobry Państwo, dzień dobry. Let us begin our seminar, and today it is a pleasure for me to introduce our new speaker, Filip Morawski, from the Copernicus Astronomical Center in Warsaw. Philip is very young. He entered the University of Science and Technology in Krakow in 2011, and in 5 years he graduated from that institute as a master in physics, a department faculty of physics and applied computer science. He is most interested in 4 subjects which are machine learning, deep learning, gravitational waves, and neutron stars. And after graduating the next year, in October of 2017, he became a PhD student of ZANK, supervised by Michal Beiger. And according to astrophysical database, Philip, has about 40 publications in the best journals with a lot of citations and more than 1,500 co-authors. That is because Philip belongs to LIGO Scientific Collaboration. Well, so he is young and he is very prominent now. And for today, he will present a talk which is based on the paper with Michal Beiger, recently published in Astronomy and Astrophysics, and the title of his talk is Neural Network Reconstruction on Dense Matter Equation of State derived from parameters of neutron stars. So please, Philip, you're welcome.
Thank you. Thank you. Thank you very much for the introduction. Okay, so let me share the screen first. Yeah, can you see my screen?
Sure.
Great. Perfect. 1 moment. Maybe let's do it this way. Okay, so first of all, hello everyone. My name is Filip Morawski. I was nicely introduced. And before I start, I would like to thank you for the invitation, for the opportunity to share with you my work and my supervisors, in which we apply one of the most popular machine learning algorithms nowadays, namely artificial neural network, in the reconstruction of the dense matter equation of state using different types of existing neutron star observables, such as masses, radii, or tidal deformability. So this talk will be divided in a couple of parts. So first of all, I would like to discuss, let's say, more theoretical aspects related, for example, to, at the beginning, to neutron stars. What are they? What you can learn from them? What are the observables that were like of interest in the context of my and Michal's work? And later on cover different aspects of our paper. So neutron stars. Well, first of all, they are extremely interesting objects to study, as I think all of you know about it. So they are born in the explosions of supernova, which are one of the most violent physical phenomena that we can observe in our universe. And they have like a couple of interesting features that makes them so special to study. So first of all, they are super compact and dense. They are actually the most relativistic material objects in the universe. And those features makes them a perfect candidate to be used as a kind of laboratories of extreme physics that might allow us to understand and learn about the dense matter equation of state. So what's the point of studying this extreme physics? Well, all sorts of interesting physical phenomena related to superconductivity or superfluidity might happen in neutron stars. Unfortunately, terrestrial experiments such as Large Hadron Collider do not allow us to probe such high densities as those required to basically understand the underlying physical processes that govern the way the neutron star works. And here is just like a very schematic example of how much lower the LHC density range it is comparing to neutron stars, like orders of magnitude. However, to learn something about the equation of state, about what happens inside the neutron star, we need a way to link somehow the microscopic and macroscopic world, because we have like a set of parameters such as pressures and densities that might be used to describe the equation of state. But what we can observe via some astronomical observation or gravitational observation are basically macroscopic properties of stars, such as masses, radius, or tidal deformability. And the way to tackle this problem is, for example, via Tolman-Oppenheimer-Volkoff equation, which is presented here on the slide, which nicely connects those two worlds. Additionally, you can include some studies related to tidal deformability of the star, and that's also what we did in our paper, by using the Love number, which is the function of stellar parameters, and thus the equation of state itself. Okay, so now we have a mathematical tools or background allowing us to connect those two worlds, micro and macroscopic. However, the next step we have to tackle is our observations. So, okay, with TOV equation, we can convert some equation of state that we model into the relation between mass and radius, for example. But now, how we can compare this theoretical relation with observations? So here is a very simple example of how the observation looks like compared to the theoretical values. So with those yellow and pinkish areas are denoted just two observations. And first of all, what you can observe here is the fact that the uncertainties, for example, in radius are quite high. They're actually so high that it will be really hard to distinguish those presented models here. So over time, we'll have more observations and uncertainties will decrease. And actually, that was also one of the motivations behind my and Michal's work, to create a method that sometime in the future might allow us to utilize this data, utilize this information about the observation, and learn something about the underlying equation of state. So one of the example of let's say experiments that allow us to collect the data and observe neutron star is a NICER experiment, which stands for the Neutron Star Interior Composition Explorer. So that's a satellite aboard the International Space Station, which uses X-ray timing and spectroscopy in order to do some research on rotation-powered millisecond pulsars. So the way that we can learn something about the astrophysical parameters such as masses and radii based on the data collected by NICER is via pulse profile modeling. And that's a technique that probes general relativistic effects on thermal emissions from hot regions on the stellar surface. How does it work in practice? Well, imagine that we have a model of the star with some surface. Somewhere on that surface, we have some hot spot that emits the X-ray radiation. Since the star rotates, the light curve that we observe will modulate, and we can observe this modulation of the star of the profile. And also, depending on the star size, its mass, the profile will change. So first of all, in this pulse profile method, we have to have models of this light curve. Then We collect the data, so pulse profile data with phase and energy, and we combine those two worlds altogether. And via Bayesian inference, we can get a notion of posterior distribution of astrophysical parameters such as mass and radius. So here's an example of results obtained for pulsar J0030, which shows more or less how those posterior distribution in mass and radius looks like and how they correspond to the equation of state, and also more or less the area of this hot surface of hot region on the surface of the star. So as you can see here, well, the uncertainties maybe are not the smallest, but generally speaking, as for the pulsar data, they are pretty small. And over time, we can hope that they will be even smaller, so we can have even precise information, even better constraints of underlying equation of state just by using electromagnetic data.
Yeah, and may I ask a question?
Mm-hmm. Yes.
The range of equations of state, the boundaries, the upper and lower boundaries, can they be made wider in some theoretical models?
So just
here.
Mm-hmm. So just to rephrase the question, if I understood correctly, so you asked if those areas of equation of state, let's say parametric space can be made larger.
Yeah, how do you plot these areas?
Okay, so
the upper and the lower curve in the equation of state among equation of state curves.
Okay, so as far as I understood, so the way that the equation of state can be produced out of those posterior distribution is via inversing Tolman-Oppenheimer-Volkoff equations. Maybe Michał could add something here more, because I am not really too specialized in this regard of nicer data. Nevertheless, that's how I understood the way it works. That just by, for example, inversing the equation and, in a sense, processing the uncertainties from one range of parameters, like the astrophysical one, into microscopic ones.
Yeah, I understand this. But you present here, the upper figures. They show some regions of parameters which are possible, determined from observational data, yeah?
Yes.
And they present also theoretical, this strip, green strip, is filled by theoretical curves, which are more or less realistic equations of state. Yeah?
Yes, I think so, yes.
Okay, so the upper and the lowest curves, do they correspond to some, most unrealistic theoretical models, or they are, produced in some other way?
Yeah, well, I think that they just, correspond to, I am not sure if I could say non-realistic models. I would rather say that just the range of models, but that still corresponds to the data in some regime. So I'm not sure.
I think they were chosen this dashed lines, right? So I think these are the prior choices, and they more or less, I think they correspond to some kind of boundaries of the region that we think is realistic. Yes. But I'm not sure that I remember exactly how they were chosen, because of course they could be chosen in many ways. But the thing is that the prior choice should not have an influence, right? Because if the data contains some information about the subject of our study, then the prior should vanish at the end, and we should have only the posterior distribution. But answering your specific question, I think this is probably taken from those previous estimates of radius and masses, like Feyerabend, Ozel, and other people were doing, this kind of very broad regions that are broad enough so that we don't miss anything in some sense.
Yeah. I think actually that this light green region is so it's matched to chiral EFT at low densities and to something at high densities, and then the left it's piecewise polytrope model, as we see is PP, right? And in the right is there are some constraints of the speed of sound, these are theoretical curves. And what you say about the posterior is operates only in the red region, right? So you actually constrain the red region, inside the red curves and upper panels, right? And then under these theoretical, interpolations, because these are interpolations like piecewise polytrope, you then extrapolate this constraint of the whole range of density. So this is not like the prior doesn't influence. It doesn't probably have less influence. In the region there is energy density, not energy, so just densities. Logarithm is 14.8, and the pressure is, logarithm of pressure is 35 or something like in the red region. But of course, in all strips to the left down and top right, your prior will influence much more. So it's, I think.
Yeah, and I think that in that source that I cite here, so this Reich-Makers et al. From 2019, from where this plot was taken, they also presented slightly different results. I'm not sure, I don't remember if it was for different models or also different priors. But yeah, they presented different those posterior distribution that that the potential equation of state might relate to this observation of the pulsar. So yeah, I think you can find more details in this topic on that paper.
So that in principle you can find in the literature theoretical equations of state which are out of this green region.
I think so.
Higher pressure and with lower pressure. Theory as well can do anything, can explain anything, all observational data.
Yeah, I think so, because that would be the point of this analysis, as I imagine, because if you get some posterior distribution of parameters in this equation of state, let's say density and pressures, you would like to relate it somehow to some of existing equation of state, and for example exclude some models that do not agree at all with this posterior distribution as maybe not feasible or not actually physical, because the data claim that it's a wrong model. So I'm pretty sure that they have to put here those models of equation of state that are astrophysical, and they have to correspond to some parameters that are physical. Okay. Thank you for the discussion. It's really nice. Okay, so the next, let's say, brick that our paper requires in the understanding are gravitational waves. So gravitational waves, which are distortions in the curvature of space-time caused by the accelerated motion of objects, and they propagate. I like these comparisons, and they propagate through space as ripples in a pond after tossing a stone into it. So currently we distinguish 4 types of gravitational waves, depending on either we know its waveform and whether the signal is transient or not. So first of all, we have the coalescing binary system, so the ones that we already detected. So the mergers of black holes, neutron stars, or the mixed pair of it. And the cool thing about this type of radiation, gravitational radiation, is that because of GR, we know the exact waveform. So it's, let's say, relatively easy to search for it in the data, but also to infer astrophysical parameters from the detected signal. The second type are the continuous waves, which might be emitted by non-spherically symmetric sources, such as neutron stars with some deformation on the surface, or the oscillating stars as well. There are also core collapse supernova explosions, because they are most likely also non-spherically symmetric. However, the problem here is that we don't know the exact waveform yet, because simulations of this phenomenon is pretty complex. Nevertheless, maybe at some point in the future, we might still either further develop models or just find it in the database by some, let's say, new techniques of data analysis that are also under development. And lastly, there is stochastic background. So the background of gravitational waves that might be primordial, might be too far from us to be distinguished from each other, or it might be like a fingerprint after the early universe, similar to the cosmic microwave background, but much older. So the unique feature of gravitational wave is that it stretches and squeezes everything in their path. And actually that's what makes them also detectable. However, this effect is extremely little. For example, over the distance of 4 kilometers, the relative change will be equal to more or less some subnuclear values of 10 to the power minus 80 meters. So the way we detect gravitational wave is that we use interferometers that were also in the past used to study the speed of light. However, of course, our version is much more advanced and bigger. So the core principle is the following. So we have some laser that shoots the beam of photons into the device. On some partially transparent mirror, the beam is split into two parts and goes to two arms of the interferometer. Inside so-called Fabry-Perot arm cavity, the beam of photons travels forth and back hundreds of times to increase the relative distance that the total distance that the light travels. And at some point, it's being transferred through this, again, some partially transparent mirror, and the interferometric patterns are checked on the photodetector. The problem is that with the detection of gravitational waves is that this detector is extremely sensitive to detect such a tiny differences in the differences in time of light travel. So those detectors detect nearly everything, like vibrations of tectonic plates, waves on the sea, rainfall, people working nearby the interferometer, but also some electronic noise of the devices that constitute to this instrument, or even some photon noise or the vibrations of the atoms on the mirror. So everything matters here. So in this noise-dominated detector, one need to use really sophisticated methods of data analysis to extract the gravitational wave from the data and learn something about the underlying astrophysical parameters. So, yes?
Are you involved in this work which is connected with the processing these gravitational signals?
Okay, because yeah, I'm going to tell about it in a moment. So
okay,
let me continue. Yes. So so here's an example of the very first detected gravitational waves from two observatories in US. So on the top panels, you can see actual data, and on the bottom one, you can see waveforms from numerical relativity. And you can ask how closely they map actual data, which shows how powerful GR is. And I mentioned this like gravitational wave, let's say, aspect here, because the way to infer astrophysical parameters, which are, for example, necessary to compute mass or tidal deformability of the neutron stars in the merger system, is from the shape of the waveform. Because typically what's being done in those type of study is that you use so-called matched filtering to search for the signal in the data. So you have some assumed template, and you search for this template in your data. And usually have like a bunch of templates that might fit this detected gravitational wave. So this will give you like a distribution of astrophysical parameters that correspond to this particular detected gravitational wave. And that was also the case for GW170817, where this was like the event of merging binary neutron stars that we are able to detect also with electromagnetic observatories. And only this one event gave us some, again, some distribution of potential range that the masses and the radius of those neutron stars might have. And again, since we are similar to NICER, we could translate those distributions into the equation of state and constrain it even further. And what's really nice thing about both worlds, so electromagnetic observations represented, for example, by NICER, but also gravitational wave like LIGO and Virgo, is that we can combine all those efforts to analyze the data to constrain the equation of state altogether. So we might have, let's say, information from a few different angles about the same source, about the same event, which is really extremely great tool in understanding what might happen in neutron stars. So that's actually why I mentioned about those gravitational waves, because this will be the source of data that you will hear in a moment in our project. So either observational one, like for example, the one you can have with NICER, but also the ones you can have from gravitational waves. So yeah, I think that we can go to the next part if you don't have any questions, or we can return later on to this discussion. So the last theoretical part before I start discussing the paper is about the machine learning. So machine learning is a really interesting field of science, somewhere between mathematics and computer science. So the goal of this field is to create algorithms that can learn from examples from the data without the need of being explicitly programmed. So this is like a very simplistic concept of how machine learning algorithm works. So you create some ML model, whatever it is. And the aim of this model is to solve some problems, solve some, let's say, hypotheses. You want to classify the images of stars, you want to compute some astrophysical parameters out of your signal, or you want to reconstruct the equation of state. You need well-defined hypotheses for the machine learning in general to work. Then you need some data that this ML model can learn from. We call it training data because it's used to train the algorithm. Then you need also some test data, because that's different from the training one, because you want to check how your model works on unknown previously samples. If it was trained correctly, if your data was training data was representative, all should end well, and more or less the results of your machine learning model should work the same on both data sets. The last thing you need to include in this, let's say, training loop is some kind of metric which will tell you how efficient your model is, what's the performance of your model, or what we call a loss function. And you feed the information about the loss function into the machine learning algorithms. And iteratively, you want this loss function to decrease or the performance to increase, depending on the way you want to describe this, this behavior. And over time, if the model is training correctly, you will see a decrease, for example, in loss function. So one of the most popular machine learning algorithms nowadays are artificial neural networks. And as the name suggests, it's a type of algorithm that tries to mimic biological neural networks. So the way it's constructed is the following. So we basically have two parts of ANN, so-called nodes that represent neurons and connections representing synapses. So the neuron or this node is in fact a function, usually a nonlinear function that's responsible for transporting the input signal into the output one. If, for example, the sum of your input signals or those connections, called also weights, is smaller than some predefined threshold, then the algorithm knows that, let's say, this information is not relevant to solve the problem, or it's not relevant for this part of the network. You can think about it the same way as human brain works, that part of the brains are activated when we listen, when we sing, when we dance, when we try to solve some equations, whatever. But the thing is that usually different parts of brain work are activated when we are doing different tasks. And that's more or less mimicked in ANNs. With ANN, we can create all sorts of custom-made architectures to solve your particular problem. However, some of them have unique names because they are well-known and they are a really great tool in particular problems. The one we used in our work is called autoencoder. Autoencoder is a type of artificial neural network that allows you to put it simply, compress your data. Imagine that you have like here an image and you want to compress the dimension of this image into some low dimension latent space, like 2 dimensions. And in this latent space, you preserve all the crucial features that are necessary to describe your input. So the second part of autoencoder might be used to recreate your data as closely as possible. You might improve the way autoencoder works, for example, and focus on the noising. So at the input, you have noisy signal, and at the output, you have pure signal without the noise. Autoencoder is also capable of doing this sort of analysis, or you can use it to recreate some equations, like in our case. We have some data, and you want to recreate slightly different data, but connected in some way. So some people describe those autoencoders or generally ANNs as multidimensional fits, nonlinear fits that are able to process really or search for some relationships in really complex data, which we wouldn't be able to do from an analytical point of view. So that's all about the theory. And now let's say the juicy part, the main part, which is our paper about the reconstruction of the dense matter equation of state. As I mentioned some time ago, the motivation to do this work was to create some methods, alternative method to currently used Bayesian inference that allows to reconstruct the equation of state using some observables. And in this project, we wanted to consider a few different aspects related to this study. So first of all, what's the influence of the neutron star mass distribution on the reconstruction of equation of state? What's the observations number and the measurement uncertainties? So the things that are really important in the data analysis to learn something about the equation of state using those observations. Additionally, we wanted to check if ANN could be used in this small project related to reconstructing the radius using only gravitational observables. As you maybe remember this slide with tidal deformability, the tidal deformability and radius are connected, but in not very straightforward way. The relation is pretty complex. And we hope that maybe you can somehow simplify it, of course, including this effect of observations number, uncertainties, and so on and so on. So, as I hope now you might understand it better, the concept of this work was to take observables, so values of masses and radius or masses and tidal deformabilities, put it into autoencoder, and reconstruct values of pressures and densities, so the equation of state, and check how it works in different configurations of data. The data that we used was relatively simple.
May I ask?
Yes.
So why your observable is, as you say, M over R or something like this, while it is not actually observable? So if you use this kind of tool, why do not you start from the actual observable, from spectrum, from wavefront?
Well, in principle, you could do this. We just wanted to start from this concept. Yeah, I totally agree with you. You can, in principle, try to put here like anything.
Well, but, I mean that because then you go, for instance, in a case of NICE, right? From the actual signal to the M or the R, there are a lot of assumptions, free hotspots, quite unusual configuration with well, quite strange shapes in some cases, right? So elliptic one and some, well, all in one hemisphere. So when you use such a, well, technique like well, black box reconstruction, the neural networks, so it, well, seems more natural to, well, try to avoid these
yes and no
additional steps.
Yes, so I agree with you. I agree with you, and you could also try to do the same, for example, with gravitational wave strain data, which is like raw data collected by interferometer, or try to convert it into spectrogram or something. So actually, the thing here is that when you want to use such raw data, it's pretty hard to remove this excessive noise to correctly compute the pressure density. There are various approaches to process this raw data, and then you speak about deep learning because the models are usually more complex. But let's say it's quite non-trivial to realize this goal. In this particular configuration I present here, it seems that it's slightly easier. And at least it's worth to check at the beginning. As a next step of your analysis, of course, you can consider an alternative approaches.
Thank you.
Thanks.
If I may comment on this, so this M of R was, from my point of view at least, was something like a secondary goal because I was mostly interested in the relation between masses and tidal deformability, because this is directly computed from the waveform, from the data, from gravitational wave data. Masses we have basically immediately because this is the first order post-Newtonian, or even not even first order, it's Newtonian term in the waveform. The chirp mass gives us the function of masses. So we have masses almost immediately with very high precision, almost, let's say, for the strong signal. And then there is this tidal deformability. So indeed, so this is in some sense, of course, a product because we have to apply the model in gravitation, so general relativity, and so on and so on. And one can, of course, go one step back and, for example, use the autoencoder to denoise the gravitational wave strain, recover the waveform, compute these things, masses and tidal deformabilities, and then apply it again to autoencoder and recover the equation of state. So there are many ways of doing this. This is probably the easiest, the most simple way. But of course, one can go more to, let's say, upstream to more raw data. But then I think there are problems related to proper training of the well, in the case of supervised learning, supervised training, how to properly train this neural network so that it understands that this data contains information, right? I believe this is also this curse of dimensionality. There is a lot of data, but this data may be kind of not obvious for the preparation.
Okay, but will you tell us how do you train your network?
I think Philip will tell us.
Yeah. So basically, we have some observations at the input and the output are just corresponding values for pressures and density. So the data we used was relatively simplistic because it was a relativistic polytrope, piecewise relativistic polytrope, and the reason behind is that we needed large data set, training data, covering relatively large parametric space. And with relativistic polytropes, we could generate as much data as we wanted. And for the low density part of the EOS, we adopted basically one of the existing astrophysical model, SLY4, up to particular baryon density, which was also changed during the computation. So the concept here is the following, that we use in total 3 polytropes connected with each other to cover as big the parametric space as we wanted. So then, as I mentioned, we wanted also to include some studies related to neutron star mass distribution, because the
Yeah,
real one, yes.
May I ask, these parameters, gamma 1, gamma 2, 3, and N1 and 2, they were variable?
Yes.
Yes. Thank you.
They were, yes. So, as I mentioned, we wanted to include some studies related to neutron star mass distribution, because the real one is still unknown, and we used two approaches here. So one, uniform, because why not? And the second one, the double Gaussian distribution, which seems to be a correct distribution based on the observations from our galaxy, with this main peak around 1.3 solar masses. And additionally, we limited our study to the range 1 to 2 solar masses. So,
sorry, and these observed masses are from binaries or from all possible sources?
Well, when we speak about the gravitational waves, I think it was binaries.
Well, for gravitational waves, there cannot be, I think. I mean, you mean the double pulse or something like this. In this sense, gravitational waves, right?
Yeah.
So all these data are from the uniform source, like the timing of double neutron star binaries, or from different sources.
I think they are all the possible masses that we have with reasonable precision, right? Because we have the first peak around 1.3, obviously relativistic neutron stars in binaries, and then there is the second one, the higher region, higher masses, and these are those ones that are around 2 solar masses. So Demores et al. And so on, right? Because they are measured, so they are also probably coming. They are produced in a different way in those pulsars, those neutron stars. But nevertheless, we observe such masses, so that would be, well, one could probably disregard them because maybe they don't enter into binaries and then they don't contribute to gravitational wave emission. Although there is this 19.425, right? Because I mean, so I'm just saying that one could use this argument that we observe only in our galaxy only relativistic binary neutron stars that have those masses of around 1.3, 1.4, like Chandrasekhar mass, right?
No, I think that's not so, because there were quite a few binary pulsars which are very asymmetric, like 1.1 and 1.8, something like this. There are a series of works by Freire et al. Something like this. But I maybe reformulate my question? So, what is the source of this plot?
So I think this is from the work of Elsing et al. 2018 or 17, I think.
Yeah.
Yes. Right?
Yes. Yeah. So, well, that's the plot I made, but I used the values from this work to recreate.
There are also binaries of neutron stars and white dwarfs, very accurately measured masses. With white dwarfs.
Yeah, but we only focus on neutron stars here.
But there are neutron stars. Well, there are binaries which contain a neutron star and a white dwarf. And these masses, they are measured very accurately.
That's right. They are like systems like this, but it wasn't, let's say, relevant from this point, from the point of view of this analysis, because we just wanted to collect samples with, let's say, observations with basically three values: tidal deformability, radius, and mass. Because, like, for now, let's say it's something that we might not have, but in the future, once we'll start collecting more data, especially those gravitational wave related, that's something that was the environment we wanted to mimic in this regard. Okay, so maybe let's go further. If there are no more questions about this aspect, okay, perfect. So that's the example of the data we prepared. So in the background, you can see those MR and okay. So first of all, instead of using the tidal deformability, we decided to introduce something we call tidal radius, which was like a transformed tidal deformability in such a way that we had basically the same unit and similar range of values as the radius covers, just for the simplicity of further analysis. And those gray curves in the background that you can see are the theoretical relations corresponding to those polytropes that we've created before. And those red points are the observations that were created after applying the neutron star mass distribution, the different number of observations, and measurement uncertainties. So that was actual input to our autoencoder. So the problem with the generally machine learning is that it's pretty tricky to address reconstruction errors, because the model itself do not contain this, like the machine learning model does not contain this information explicitly. You need to introduce it somehow. So the way we thought we can tackle this issue was via, let's say, frequentist approach. So imagine that we had like a single polytrope, and for this polytrope, we generated 30 different instances of data, and single instances contain all the points that you saw before. So some that will differ in the measurement uncertainties, observation numbers, and so on and so on. Then all those different instances of data will be used to, let's say, to feed into the model, to the autoencoder. And so you will, at the output, you will obtain some equation of state values. Then you will compare those results with underlying values of this equation of this polytrope that you used at the beginning. And like, because you have those different realizations of your data, this will give you a notion how this reconstruction error separately for pressures and densities works.
Sorry, may I ask a question?
Yes.
How did you restrict these parameters? There are the parameters N1 and 2 and gammas to vary. So when you are varying, you should restrict them somehow within some limits.
Yeah. So Michał, do you remember what is exactly what each part corresponded to?
So we basically generated a lot of those equations of state. Then we have calculated mass radius curves, and basically then restricted the parameters such that they basically cover this region, which is kind of like realistic, let's say, in the first approximation, so that we have let's say between 10 and 13 in kilometers radius, masses like that, like on this plot, so that it also covers this region that we are interested in, that of those realistic equations of state. Because of course, if we would change this training data set, then we would teach the network something else, and then maybe our reconstruction of this realistic equation of state will be different. So basically we did it by eye. Basically that's the answer.
Okay.
Just to have something kind of reasonable. Yeah.
Okay.
Yeah, exactly. So, and here is just a comparison of how does, let's say, a bundle of those MR relations and its corresponding polytropes related to, let's say, the astrophysical equations of state that we chose for the final test. So SLY4, APR, and BSK20. So first result I would like to show you is how the performance of artificial neural network, also called loss function, as I said before, changes when we change number of observation or initial input, this measurement uncertainties. So as a loss function of our ANN, we used mean squared error. So to put it simply, the lower value, the better model works. And first of all, you can see here that in all studied cases, so the left plot is for the reconstruction on electromagnetic data, so masses and radii, and the right one is on masses and tidal deformabilities. So basically, in both cases, it works similar, and the most significant impact were associated with measurement uncertainty. And it made perfect sense because the higher the uncertainty at the beginning you had, so the more scattered those points were around those theoretical values. So it was harder for the model to recreate like a smooth equation of state. So obviously, like those reconstruction errors should increase, and that's also what you are going to see in a moment. But interestingly, like number of observations did not affect that much this type of analysis, the performance of ANN, which meant that even for smaller number of observations, and we studied between 10 to 50 a number of observations, the model seemed to work similarly. It's also a good thing because in the future we could, use it sooner when we will have even, let's say, 10 or something, 10 or 15 observations, for example, from gravitational waves. Okay, so here is the first example of the reconstruction of equation of state. So first of all, the electromagnetic data, so mass and radius on the left and the left plot, and two extreme cases. The red points are the smallest, contain the smallest of measurement uncertainties, and the blue one, the bigger ones of considerate. On the right side, you can see how well the reconstruction worked. And in both cases, it seemed that the reconstruction is really, really good. Even though the reconstruction errors, so those bars in pressures and densities, you can see, increased proportionally, which was like quite a thing you can expect, because these are the results for the double mass Gaussian, for the double Gauss mass distribution, which means that you will have, let's say, less samples around the massive stars, so close to 2 solar masses. And since you have less samples there, then you will also have less points on the equation of state that relate to high pressure density regime. So the uncertainties, like the reconstruction errors, have to be bigger. So this is a test on the reconstruction of astrophysical equation of state, which works very similar as to the one on the polytropic dataset. In case of SLY4, we could see that those points are slightly off the theoretical value, but still, at least in those reconstruction errors, they work well. And anyway, when you focus on this lower pressure density region, the reconstruction seemed to be really, really good. Similar results were obtained on gravitational observables. So you have here the mass and tidal radius on the left side, and on the right side, corresponding reconstructed equation of state. Again, very similar behavior with this proportional increase on reconstructed errors of pressures and densities. And the final test on the astrophysical equation of state. In this case, the SLY4 case, at least for higher pressures and densities, well, it seemed to be not too much correct, but at least this lower part, again, was good. But we weren't like happy enough with those results, and we wonder what would happen if you would change the neutron star mass distribution to more uniform to cover this high mass range. And that's what happens here. As you can see, the reconstruction errors substantially decreased, and overall reconstruction of the equation of state was much, much better. Well, again, beside this highest pressure density regimes, but again, it's fine because to actually probe well this high pressure density regime of equation of state, you would need really a lot of samples around this high massive stars. And we didn't consider such a mass distribution. So that would be a potential solution to the problem, but not really like physical.
Please excuse me, may I
yes.
Briefly ask some naive question? What is the meaning of those labels 1E36 and 1E15?
Okay, so it's like a scientific notation, so it's 10 to the power
I understand.
Mm-hmm.
What those numbers mean with respect to the data.
So it's just the range. Okay, I should put units here. Okay, that's it's here. Like the units, it just corresponds to the range of pressures and densities that those equation of state were basically.
So those labels near the axis should be multiplied by this.
Yes, exactly. Yeah.
Okay. Yes. Okay.
Yes, sorry.
Thanks
for the confusion. Yeah.
Thank you.
Okay, thank you very much. And this side project we tried was, which I mentioned that we wanted to do, was the reconstruction of the neutron star radius. So again, two cases: low measurement uncertainties, high measurement uncertainties. On the left side, you can see the, let's say, the input data, so mass and tidal deformability or tidal radius, and on the right side, mass and radius corresponding. Well, unfortunately here, you could see some fluctuations, especially in this second case, on this blue line. But nevertheless, the reconstruction of those corresponding theoretical relation was quite accurate, also in case of this, let's say, astrophysical equation of state used to generate those data. So yeah, we're quite happy because we didn't expect that this will kind of work, especially since the relation between those two are not so straightforward from an analytical point of view. And yeah, I think that's the summary of the talk. So our methods allowed to reconstruct the equation of state using both types of data or observables that we studied in all considered cases. It turned out that the neutron star mass distribution plays quite important role, especially in this high pressure density regime. And lastly, the reconstruction of radius based on gravitational observables was quite decent, though you had those fluctuations, like it seemed pretty random in the end on this largest of studied measurement uncertainties. One thing I would like to add here is that, well, we didn't consider phase transition here in those equations of state, since we assume that it will be slightly harder for the ANN to reconstruct it, but that's something we are trying to do now. So it's like a second part of this project. And yeah, we are generally like trying to address the question if machine learning could be used to say something about the presence of phase transition using the data. But that's rather something we are going to maybe present at some point in the future when our analysis is done. So thank you very much for attention. And yeah, if you have more questions, I will try to answer them as best as I can.
Thank you very much, Philip. Well, now, please ask questions.
Philip, you said that your possible range of the masses is restricted to the range 1 to 2 solar masses. How sensitive will your results be if you choose the upper limit to 2.3, 2.4 solar mass?
Okay, well, so in fact, like maybe I wasn't too specific here, because as you can see here, there are like some samples that are slightly more than 2, but this is because of measurement uncertainties. So that's the first thing. But the second thing is that when we take a look at the equation of state, well, any kind of equation of state, the thing is that when we increase this, maybe let's do here. When we increase the maximum, let's say the range of masses, then we'll find we found problematic to reconstruct the equation of state, because we did it. Like at some point, we were trying different ranges of masses, and the problem was that the higher the mass was, let's say the bigger the differences were in this in the domain of pressures and densities. So the reconstructed errors in this high pressure density regime that corresponds to high masses were really, really high. So, and it affected actually whole reconstruction, that overall the reconstructed errors increased for like the whole reconstruction. So we had to limit ourselves if we wanted to like preserve this decent reconstruction. That
this is actually strange. It should be the other way around. If you have a very large error in some high ends of your plot that it should not in any way affect the lower part of the plot. Why if you have for high density some larger error, then it basically means that you have no data there. So why it affects the whole reconstruction?
Well, if you imagine the following: that at the input to your data is like a set of observations, so masses and radii. And at the output, you have the corresponding values of pressures and densities. And the bigger the differences between say they are more separated in the pressures and densities domain. So overall, ANN performance, because it's computed for whole model, will decrease. So when you take a look at those,
if you have the same free observations, same number of observations, say 5 in one case and 5 in other case, but you shift one of them to the higher end.
Yeah, so imagine that, okay, you have 3 observations and all of them are, let's say, corresponding to high mass end, like around 2.3. But since we are randomly choosing those values, so let's say every time you would have slightly 3 different values. And even though the differences in the mass range would be small, the corresponding differences in the equation of state could be in principle very large. So
right, but you have all other observations in lower end. Mm-hmm. Then you have a limit of two solar mass. Then the question of Misha was if you shift this limit to the right. Right, so that means that hypothetical future observation finds your star at 2.3. But all other objects are there. So this star, if it have large errors, it should not affect your reconstruction at low densities.
No, at lower, no.
What you said, the whole reconstruction is affected, but this is probably the case if you disregard all the lower part and compare just these only high mass range.
Okay, so let me clarify what I meant by whole reconstruction will, let's say, decrease, because here is this loss function which defines a total performance of ANN. So when we started to expand the range of solar masses, like to higher values, the overall MSE, so mean squared error, went higher. So you could say that overall reconstruction capabilities of ANN was lower. And ANN...
Right, for same number of observations, right?
For same number of observations, yes. So it means that overall, because this MSE is computed between the ground truth values of pressure densities, so your expected output, and your reconstructed output. So if your ANN is higher, it means that differences between those two groups will be larger overall. Because from ANN point of view, it doesn't really matter, which values are corresponding to a low density pressure range and which to higher. It's just a number. So, and they treat it all together at the same time, because the information about the information, the input is processed at once through whole network. So that's why you might see this decrease in reconstruction errors. No, increase. So they are worse as a result of overall increased mean squared error, because the network had to cover a larger range of parameters in the pressure density region. That's just how this approach works. Since you have one metric, it will be, let's say, if it's worse, then this worsen effect will be spread across all samples that you're analyzing.
This depends on metrics.
Depends on the metric. That's right.
May I ask, have you tried to increase the number of pieces of polytropes?
Well, actually not. We started from 2, and in the end we stayed with 3 because 3 was enough to create some representative set when we compared it to some of the astrophysical equation of state. We had more, like 6 or 7 those equation of state, but in the paper we just put 3. And yeah, the 3 was enough to create something that was, let's say, representative from statistical point of view.
And have you tried to fix, for instance, N1 and N2 and change on the gammas?
No, we didn't try it. We didn't try it.
Okay.
Well, actually, maybe it was partially done because we were changing those values iteratively. So for every N0 fixed, we changed like other ones. For every N0 and N1, we changed other parameters and so on and so on. So there were some cases that had basically only one parameter changed and the equations or 2 parameters changed. It was like computed iteratively. So partially it was included in the way the data was generated, what you meant.
And there is actually no difference, yeah?
No, there was no difference, yes.
Okay.
No difference.
Okay, thank you. More questions?
Okay, Misha, okay.
Correct me if I'm wrong. So you describe the equation of state by some 7 parameters?
Yes. 6 or 7 in total, because you have those 6 here. And I think there was also something related with potential phase transition, but let's say this parameter was turned off in this type of analysis. But yeah, like let's say that at least 6 parameters were used to describe the equation of state.
Okay, thank you.
I also have a question. Can you hear me?
Yes.
So I don't get why you need to use machine learning approach. What advantages does it gives in comparison for the, I don't know, Bayesian style of between this? Because it's too complex. You don't need. I don't see the data. Real data did not force you to use machine learning, I would say.
Well, so the main motivation was just curiosity. Well, because why not? We can maybe try something different, but that will allow us to achieve, let's say, at least similar or the same, or even maybe better results. So we're curious, maybe it will work better. It's definitely faster because machine learning, once you train, it's the fastest basically technique you can apply to your data analysis. And yeah, like it works also quite well with measurement uncertainties, and those Bayesian inference methods are quite sensitive to how uncertain your, let's say, your input data is or might be. There were like a couple of reasons to try it.
But I mean that, for example, to do faster, you don't need, if you have not too much data, and as I understand in this case or this measurement, you always will have several data points. For example, I don't know, you don't expect that you will have a very large data set, so I don't see the point to use. At least it's my impression.
Yes, I agree with this comment by Sergey.
Yeah, well, in the end, we were just like, let's say the main motivation was curiosity. Like if you can try some alternative methods, at least in my opinion, it's good to try new things and see how they work with, let's say, alt data, alt approaches. And maybe in the meantime, you can figure out that some method that might work better. This was like a first work as a proof of concept of general analysis that in the end aims to check if machine learning could potentially say us something about phase transition. So maybe like, you know, in this regard, you could see a potentially like some potential in this approach, which is more kind of, let's say, I don't know, maybe obvious or at least worth to check if machine learning can tell us something, whether there is a presence of phase transition or not.
Yeah.
Can I? Well, I want to clarify one point you made. answering this question. So you said that the say likelihood methods have some problems with the measurement uncertainties, and the machine learning, as you said, has less problems, right? What did you mean exactly?
Well, that's like what I meant is, for example, here that even here, maybe just by checking like how the results looks like that. What I meant is that machine learning in general, or at least artificial neural networks, are pretty well in dealing with the data that contains some noise. Actually, by having some noisy data, some noisy samples, you might even make the method work slightly better than you would just feed it with some smooth.
If you are pretty sure with your model, right?
Yes, of course, yeah, that's right.
But even the piecewise polytrope of 3 segments is not the true model, right?
No, it's
so how do you?
Yeah.
So if you have the noise, you know the noise properties, or at least you think you know that your errors in the left panel are Gaussian, I think. So then how can you make better read of the noise by some inversion methods? This is I think I cannot get.
Well,
so
like
you need to estimate the noise and estimate the model. So basically you can, I think, prove that by some traditional methods, the statistical properties of these estimators, right? So, and I think that you cannot go better. If you have uncertainty, it will be, consider linear regression. If you have uncertainty in the data, the noise, which is physical noise, then it is will be a multiplier of all your uncertainties. You cannot use any method to reduce these uncertainties because it's just how the nature is made. So you have how the machine learning can be an advantage to it.
Well, to, let's say, precisely answer to your question, I would need to, in this particular case, use the Bayesian inference for the comparison and then actually prove that ML is, I don't know, better than Bayesian inference. So my opinion was rather based on the works of the others and generally from machine learning community that this in some cases machine learning is definitely a method worth to try with some data that might contain some noise, and if you want to, let's say, smoothly reconstruct, like in this case, some values that might relate to some equation, or generally to search for some patterns. Maybe saying that maybe it's better than Bayesian inference. Yeah, maybe that was too much because I haven't checked it, to be honest. But as for me, it's just
not necessarily Bayesian frequentist inference. So, but I mean, if you have the, say, probabilistic model in any case which you want to invert. So you have the process, that you have the model, and then you get real data. You add the noise. So you want to estimate the noise, and if you have the measurement errors, it will always be multiplying the uncertainty in the end, irrespective of method, I think.
Yes, you are right. Yes. Yeah, but I don't then know. I'm not sure, in which what was in the end the question here, because I agree with you. But I still say that trying new approaches to deal with even old problems like this one is definitely worth to give a try, because you can always learn something new, even about the data, about its nature, and infer some things for some future analysis, even staying with, let's say, more conservative approaches later on.
I would say what is not forbidden is allowed.
Yeah.
More questions?
Okay, so I have another one.
Yeah,
sorry.
Sorry, guys, but like, can this be a last question? Because I have a next meeting in a few minutes. So
okay. So if anybody wants to ask another question, maybe no. No. Okay. So then my question is: so you showed that is mass distribution, right?
Yes.
And I am looking in the paper you referred, so Michael sent to chat, and the result is some posterior for neutron star mass, which looks different. So the second pike is 4 times lower than the what you plot. So why you use the data from table but not the result of their paper? So these
yeah, one moment. Let me check the paper, because maybe it was just like a silly mistake. Maybe I'm like.
It's
which figure was it?
No. I mean, so I looking in the paper by Alsing, right? Alsing and Alia.
Okay, I see.
Okay, so they show, they show the table with measurement, and then they show the neutron star mass distribution, the posteriors, and these posteriors looks different from these structures. So they are 2 pike, but the second pike is much lower.
Is it much lower? Yeah, maybe.
So I don't know what is if you just take the numbers from the table, right? But the analysis of the paper, the results which are shown in a figures. So it's a figure 1 and figure 2. So they are
Yeah, well, I just made this plot before the talk, so maybe it's not, let's say, too realistic with respect to the paper you mentioned, but yeah, the one that the data that we used to create like a training data were basically taken from them. So if what you are saying is right, I assume it is that that the second peak is smaller, then yeah, we also had it in our data.
Okay.
Yeah. So that was just just to show you like how it might look like for the presentation purposes. Thank you for this, for pointing this out. Okay.
Okay, I think that, well, are there any other questions? If not, let us thank the speaker again.
Thank you very much. Dziękuję bardzo. Spasiba.
Thank you very much for giving us this.
Thank you for this opportunity.
Okay. Goodbye.
Goodbye.
Well, and announcement, ladies and gentlemen, the announcement is that perhaps in Russian. На следующей неделе семинара не будет, а в семинарское время будет устроен астрофизический совет физико-технического института. Заседание будет открытым, и все могут присутствовать. Единственное условие, что на YouTube не будет показываться это заседание. Там будут сделаны 2 сообщения, насколько я помню, но, может быть, Александр Юрьевич точнее.
Да. Значит, заседание Совета будет посвящено перспективам гамма-астрономии в физтехе. Сообщения будут сделаны Дмитрием Дмитриевичем Фредериксом относительно орбитальных проектов и Александром Михайловичем Красильщиковым относительно наземных проектов.
Ну вот.
Я не успел, но я сегодня планирую, есть некоторые срочные дела, я сегодня планирую разослать объявление.
Хорошо, тогда мы наш семинар можем закончить, а через неделю там будет семинар, где будут выступать наши японские друзья и рассказывать про расчеты сверхтекучести, критических температур сверхтекучести и модели сверхтекучести в ядрах нейтронных звезд с учетом многочастичных эффектов. Все, семинар окончен.
До свидания.
До свидания.
свидания.